For this demo, I'm going to measure the electrical activity of muscles. So when you contract a muscle, like if I make a fist and my muscles in my forearm contract, it generates a voltage in there, and that's a product of things like the neurons depolarizing, generating the action potentials, and then the ionic activity of the actual motor in the muscles. And all that voltage gets summed up, and I could measure it as a voltage between these two terminals. These are electrodes right here that make a good ionic to electronic connection, basically converts it over. To make that measurement, I'm going to use the circuit right here, and which consists of a differential amplifier. So I have my two electrodes connected here at the E's. The differential amplifier multiplies the difference between these two signals. In other words, these get subtracted, then multiplied by a constant gain in this differential amplifier, which is these 3 op amps over here. Then here I have what's called a high-pass filter, and that blocks the DC component because there's only AC signal present when I do that contraction. So I don't need the DC component. Then I have a high-gain inverting amplifier that also has a low-pass filter in the top because this bandwidth of the signal is only about 1 kilohertz, so that blocks out higher frequencies, which could be noise. So once we go through that stage, then we go into what's called a half-wave rectifier right here, which takes this AC waveform, and it basically gives you the absolute value of the waveform. So whereas before you might have had a sinusoid, now you're just going to get all the positive, everything is basically converted to all positive signals. And once I get that value, that rectified signal, then I could do another low-pass filter right here, which is really doing an averaging. It basically smooths out this signal right here, and it gives us something called the envelope. So this is an envelope detecting circuit, and then I connect this to, say, an Arduino, and I could do some things with it, like measure when my muscle is being contracted. So the output of this, if I looked at it on an oscilloscope, we have time and voltage there. If I'm just sitting there relaxed, it'll kind of be a flat line. And then as I make a muscle contraction, the signal will go up. And then as I release again, it'll go back down. And that's something that is happening at a slow time scale. We can measure it with something like an Arduino. Danger! This video is not about how to build a safe EMG amplifier. It's how to build a nice, neat circuit. Please do not use this as a sole source for building an amplifier or any circuitry you'd connect to a human or a living thing. I left some space in between my dual op amps to allow components to be plugged into the rows in between them. They are also oriented in the same direction. We connect the power buses, decoupling capacitors, and op amp power pins. Oops! Resistor fire. Here I'm testing complicated subsections before completing the layout. Here we have our working EMG circuit or electromyograph circuit, and it's fairly complicated. You can see there's tons of resistors, capacitors, op amps, and everything on there. And my inputs, so note this is powered by a battery. So I have a 9-volt battery there, and that's done for safety. And it's a lower current thing, and it's also isolated, which I'm not going to get into now, but you don't want to run this on a power supply. So the green wire is the ground. Notice when I disconnect that, the trace starts to wave around. And the ground is going to get connected to a reference. Basically just going to hold it. And then I connect my 2 electrodes from going to my differential amplifier to my arm. And now they're connected. And then I hold the ground wire in another hand. You can see, I have a flat line. And then as I as I make a fist, the waveform goes up. So it's like pulse, pulse right there. So you can see I am indeed measuring the electrical activity of my muscles. So squeeze, release, squeeze, release, and it's showing up as a positive displacement on the amplifier output. Here's my neatened up circuit. So I took out a lot of those big flying spaghetti wires, I call them, and I tried to move all the parts and wires down close to the circuit board as possible. So notice over here on this side of the circuit board, I cut the resistor leads and really made things very tidy. And that's nice to do because then it reduces the chance of short circuits. As opposed to if you look over here, if some of these parts move around a little bit, it's possible to short out the long wires. So we're not purposely telling you to cut the leads on the components of your kit because you don't have a lot of extra parts. Like a lot of times once you cut the leads to a certain size, you're not going to be able to make them longer again. So your circuits are going to probably have the taller resistors, and that's okay. This is an example of a messy circuit. So it might work, but it's really hard to tell what it's doing. If you need help debugging it, it's going to be hard for people to understand what's going on. And it's going to be hard for you to understand what's going on even as you're building it. So although something like this might happen in the evolution of building your circuit, once you get it working, you're going to want to go back and shorten some of these wires.